My name is David Hollander. I'm a professor of chemical oceanography in the College of Marine Science here at USF.
And what's your role in BP studying?
I was in part chief scientist on a number of the early cruises. Our work has been tracking the oil in water and subsequently in the sediments, and then how it translates into the ecosystem.
Well, one of the things I was reading is that you were finding that the oil is settling in the sediments. What can you tell us about BP oil settling in sediments?
Well, with the Deepwater Horizon, it being the first deep sea blowout, there were a lot of new things that had never been discovered, in which from a scientific point, in spite of the sober aspect of the blowout and the number of people killed, was that there were a lot of new paradigms to write for science. And some of them included the subsurface plume, but one of the outstanding, more long-lived results that we found was that oil came up to the surface and then turned around with a process and ultimately sedimented down on the floor of the northern Gulf of Mexico, on the continental shelf and on the slope.
Is that because of the marine snow or something else?
Well, yeah, it was a marine snow event, but in marine systems you constantly have particles that are settling down. But this was, when we named the term flocculent blizzard, because indeed what had happened was the oil and the dispersant were interacting with the algae. When they opened up the floodgates of the Mississippi and the diversionary channels to push the oil offshore, a lot of clay minerals and nutrients came out with it. And as a consequence of that, the oil bound with the clay minerals. The dispersant caused the oil droplets to decrease in size, making them more bioavailable. But at the same time, the algae, with their nutrients, were blooming, and they would secrete a mucousy material to essentially create a buffer between the contaminants and their cell walls. And that material was very sticky. So you had this perfect storm of the clay minerals, the nutrients, the algae, the oil, and the dispersants aggregating together, coming together, binding together, and then because of the clay minerals, they were able to sink to the seafloor very rapidly.
And there was a study that was titled "Chemical Dispersants Can Suppress the Activity of Natural Oil-Degrading Microorganisms." How did that work?
The jury is still out. Some microorganisms, you can't group them into one single bin. There are many microbes that actually actively degrade oil. Some prefer the dispersant, some prefer the oil. It seemed to be that the two together created a little bit more of a toxic mix than one had anticipated. But the microbes did a pretty good job of degrading the simple compounds. But petroleum is made up of over 70,000 compounds, some quite complex, and those still remain.
So what lessons, as far as dispersants go, for if there's another marine oil disaster like this, should people use dispersants?
Well, it's a fairly complex issue because there was dispersant deployed and applied onto the surface of the ocean. But for the first time in history, it was actually injected into the oil blowout itself out in the deep sea. So on the surface, it helped to cause this marine snow event, and so people should be cautious of that. In the deep sea, there is a lot of argument about whether or not it actually did anything. The aspect of the oil coming out, but oil and gas, which is what they call live oil, has a much different behavior than does pure liquid oil. And so the dispersants, they didn't regulate whether or not the plume was going to form. It formed. It may have increased some of the concentrations of it, decreased the droplet size, and ultimately made it a little bit more biologically available. So it's a real debate right now. The surface application of dispersants is used for decades, and if you're trying to help the first responders that are there, it might be better. If you are looking at the long-term impact for the ecosystem, that might not be the best choice. But the application at the wellhead itself, that's still very much of a debate. And now is the time where you have experimental work that is done under high pressure, such as that we are doing in Hamburg, where we can actually simulate those pressures, those temperatures, those flow rates with live oil and see what the impact of those dispersants are.
You're calling for more baseline studies. Why are those important? First of all, for someone who's not a scientist, what is a baseline study and why is that important?
A baseline study is characterizing the circumstances, the components prior to an event. So if you want to really understand what the quantitatively, really in hard terms, what was the impact of an event, you have to know where you were before that event occurred. And that's what they refer to as the baseline. And in the Gulf of Mexico, there were sadly very few baselines available for many different components that were affected by the spill. And that's why, as scientists, you are always hedging your bet of how much that impact, really what impact occurred and how severe was it, because we never had the kind of baselines that we needed.
Some groups are calling for a moratorium on deep drilling. As a scientist, you probably don't want to wade into the politics of it, but from a standpoint of the health of the ecosystem, what would you say?
Well, I think the reality is that we are a hydrocarbon-driven society. The fact is that there is an increasing tendency for the industry to move into deeper and deeper and deeper water. About 40% of the oil recovered out of the Gulf of Mexico today is from ultra-deep wells. The engineering is phenomenal. They are very capable, very proficient at what they do. The interesting aspect is that these events occur very rarely, but when they do occur, that's when there's the possibility for catastrophic impacts to the ecosystem. They're drilling now in over 2 miles of water, so 6,000 meters, about 5,000, 6,000 meters. The Deepwater Horizon was about 1,500 meters. So indeed, in the Gulf of Mexico, it's quite common to see wells at 2 miles depth, so somewhere on the order of 3,000 meters depth. And the question is, if something happens, how do you plan to shut it off? Obviously, it's too deep for any divers to go down, so it all has to be done remotely with remotely operated vehicles and through electronic communications. And so this is a debate. There is an argument of whether you want to do fracking, is that better than deep sea exploration? And that's a debate for the policy people. But there's a lot that could be improved upon in the deep sea exploration and production.
What do we know about the safety of seafood in the Gulf?
Yeah, well, the safety of seafood is probably better than it ever has been in the context that more eyes are watching. The testing is very rigorous. There are parts of the fish that still continually show contamination, whether that's chronic or a relaxation from an acute event. That's still to be debated. But it's principally in the liver and in the gallbladder, and those you shouldn't be eating anyway. If you look at or do the testing of the muscle, it looks perfectly good.
And the deformities that we've seen in Gulf organisms, do you think that might be related to the BP spill?
Well, I think that's our largest fear, is that there's actually genetic alteration of the next and following generations. And this is why you can't rush to judgment to say that the Gulf has restored itself and it's resilient. Things happen and they have to work their way through the ecosystem, which may be generational. And as a consequence, 6, 8 years down the road, things may be showing up as problems that you would not think originally happened, such as in the Valdez. It took 4 years for the herring fisheries to collapse after the Valdez. After the Valdez, fishing went on like it never had, like in the Gulf. And the question is, what is the long-term impact? So I think that's the thing that we're most fearful of, is that these impacts will result in genetic alterations which then affect generations to come.
So finally, there's still a lot of science that you're doing now. What are the biggest questions that you have yet to answer and you're still trying to look at right now?
How long will petroleum stay in the system? How long will it take for a lot of these benthic, deep, sedimentary ecological communities How long will it take for them to recover? That's pretty much the largest consequence, and of course the genetic implications.
I said finally, but since you brought up the deep benthic communities, what's that like? Most of us have never been there. What are those communities like, and how have they been affected?
So they form the basis of some of the food web for the fish, for example, that live off of food off the bottom. Some of them live on the bottom, and some of them burrow into the bottom. So if these organisms that actually are the food source for the fish continually take up contaminants, then the fish will be contaminated. I think what we're seeing, though, is initially there was a die-off because of the marine snow or the flocculent blizzard effect, and now they're coming back. It took 3 to 7 years, approximately. That's what we're seeing. We're able to judge that and compare it because there was actually another spill that happened in the Gulf of Mexico back in 1979 called the Ixtoc spill. And in our last funded proposal, we proposed to go down to the southern Gulf of Mexico, to the Bay of Campeche, where the Ixtoc blowout occurred, and take sediment cores and evaluate how long it took for the benthic system there to recover. We saw the same kind of phenomena as a marine snow blizzard effect that had occurred down in Mexico, and we estimated that it was somewhere less than a decade that it took the system to recover. So we can have the same expectation for the northern Gulf of Mexico, especially considering that the communities are almost identical to each other.
Great, thanks so much for your time.
You're welcome.